The transpose helps you one-tap a lot of linear algebra problems, so here are a bunch of transpose tips and tricks that you need to know. Okay, so what is the transpose? Take this matrix and then raise it to the power t. Okay, I'm just kidding. That's not what it is. That's just the notation for the transpose. Okay, so what have I actually done here? I've taken the matrix and kind of rotated it and reflected it in some way, but really it makes more sense if you look at it by rows and columns. I've taken the first row of this matrix and now it's become the first column, and the second row has become the second column. So the transpose just interchanges rows and columns. Maybe let's look at it by entries. The entry in row 2 and column 3. But in the transpose, it's actually in row 3 and column 2. Notice once again the switch between rows and columns. So you can define the transpose like this. The transpose of an m by n matrix is an n by m matrix, where A transpose ij is equal to AJI for all matrices A. Now, one niche example of this, which actually comes up a lot, is taking the transpose of row vectors. A row vector is a 1 by something matrix. This one here is 1 by 3 because it has 1 row and 3 columns. But a row vector is just the transpose of a column vector. You can actually multiply a row vector by a column vector. And you can see why, because this is 1 by 3 and this is 3 by 1. And since the middle numbers match, the matrices are compatible, you can multiply them. And the result is going to be a 1 by 1 matrix. You can see clearly, right? This is a dot product. It's the dot product of the vector 1, 2, 3 with 4, 5, 6, which is why we have this formula. X transpose y equals x dot y for all vectors x and y of the same size. Now, notice here, this x transpose is a row vector and the y is a column vector. There is a bit of a technicality here. X transpose y is a 1 by 1 matrix, but x dot y, well, if you remember, the dot product returns a scalar. It's just a number. Maybe this would be a bit more correct if we put brackets around this, signifying it's the 1 by 1 matrix containing this dot product. But we don't really do that. We're just going to treat 1 by 1 matrices as scalars, and that's what we really do in linear algebra, because there's not really much point treating them differently. They basically have the same properties as scalars, which you can prove. So we're just going to keep it like this. X transpose y equals x dot y. Now there is this other thing. You can also write this as y transpose x. And one way to see that is because the dot product is commutative, which means you can switch the order of x and y and it won't change the result. Now here are some nice identities regarding the transpose. I'll just list them all out here. Really, you should try proving these yourself. And I'll just give you a bit of a hint on how to get started. So you're trying to prove these matrix identities, right? How do you do that? How do you prove two matrices are equal? Well, if you want to prove A equals B, you just have to prove that each entry of A equals each entry of B. And maybe you'll have to argue that they have the same size as well, but yeah. So you just need to show that Aij equals Bij. Also, you'll need these tools: the definition of the transpose, the definition of addition, of scaling, and multiplication. A transpose transpose equals A, that's kind of pretty obvious. The next two formulas tell you the transpose is linear, meaning you can split it up over sums of matrices, and you can also take scalar multiples out. There's also a product rule. You switch the order. That's very important, especially because matrix multiplication is not commutative, so the order actually matters. Just some clarifications. In this second one, A and B are the same size. Here, lambda is any scalar, so any number. And for this one, A and B are compatible matrices. You can multiply them. And for the last one, X and Y are vectors in the same dimension. Now I'll leave you guys with a practice question. Let A be an n by n matrix, so it's square, and we have a vector x in Rn. Show that Ax is the zero vector if and only if A transpose Ax is the zero vector. Okay, so I'll just give you the first part of it because it's not that hard. So we'll first assume that Ax equals 0. Now we want to prove A transpose Ax equals 0, and it's kind of obvious what you have to do. You just left multiply by A transpose, and that would give you A transpose 0, which is 0. Now we need to prove that if A transpose Ax equals 0, then ax equals 0. So how would we show that ax equals 0? Well, there are some nice tricks to showing a vector is equal to 0. Instead of showing directly it's equal to 0, you can show its magnitude is 0. Now, why does that make it easier? Well, one way is to use the magnitude squared trick. It's sometimes more useful to think of the squared magnitude than the actual magnitude of a vector, and that's because you can use the dot product. There's this nice identity where the squared magnitude of v is equal to v dot v, which you might know. This is really useful because now we can exploit the properties of the dot product. So we're just going to show that ax dot ax is equal to 0 instead. Okay, so what now? Well, think about it. Ax is a vector. Always keep that in mind, ax is a vector. And we're taking the dot product of vectors, so we can use our new trick. We'll have the transpose of this thing times ax. It's kind of obvious to do the transpose product rule here. AB transpose equals B transpose A transpose. Now, what did we assume? We assumed A transpose AX is equal to 0. And now you can see this is just going to be X transpose times the 0 vector, which is indeed 0. And for those who know about null spaces or kernels, this actually shows that A transpose A and A have the same null space. I'll just give you some practice questions and I won't actually go through them. This is for homework, but obviously it's optional. I'm not enforcing it. It's YouTube. You can do what you want. Okay, this is kind of an easy question, so let's just go to another one. This will be a bit harder. This proves that orthogonal matrices preserve magnitude. So what is an orthogonal matrix? It's a matrix such that Q transpose times Q is the identity matrix. If that's the case, you can actually show that when you apply Q to any vector x, then it actually doesn't change the magnitude. And this is for all vectors x in Rn. Good luck with the problem. Thanks for watching. I'll see you next time.